Okay, for this question, we've got a rearrangement taking place. It's actually the Schmidt rearrangement. And it's very similar to other rearrangements to nitrogen, such as the courteous rearrangement. In fact, really, really similar to the courteous rearrangement. So the Schmidt rearrangement takes, or Schmidt reaction takes a ketone and hydrozoic acid, which is HN3. So what does that look like? So we've got hydrogen, nitrogen, nitrogen, nitrogen. Azide and azide-containing molecules are great molecules to practice drawing Lewis structures and drawing resonance forms of them. So, for example, to get good Lewis structures for hydrozoic acid, we could, for example, start with something that looks like this. Okay, so where are we going to put lone pairs and formal charges here? If we have a nitrogen with 4 bonds, like the central nitrogen here, then it is going to have a formal positive charge. Okay. Normally, to be neutral, a nitrogen would have 3 bonds and a lone pair. So it's got its lone pair, now it's sharing it with a neighboring atom. So that gives it a formal positive charge. This nitrogen atom here has 3 bonds, so it will have a lone pair of electrons and no formal charge. The one at the end here, in this resonance form, has 2 bonds, and so therefore it has 2 lone pairs of electrons and a formal negative charge. Okay, so what other resonance forms can we draw? We can draw one where we push this pair of electrons in like that. That would give that central nitrogen 5 bonds, so we would need to keep on pushing electrons like that. And we can draw a resonance form that looks like this. That's the negative charge on. I'll just draw that out again. Okay, so that now is another resonance form of this molecule. Now, another thing to recognize about this particular molecule is that it's called hydrozoic acid because it's acidic. So it has a pKa, depending on what source you look at, of around about 4.6. So it's not, incredibly acidic, but it's similar to carboxylic acid, so it can act as an acid and protonate species. So what we can do is take our ketone, and I won't do it on these resonance forms. I'll just draw it like this. We can get lone pair of electrons on that ketone and attack the hydrozoic acid and kick out azide as a leaving group. Now, unfortunately in organic chemistry, we quite often get a bit lazy with how we draw some of our arrows. So really, this is an equilibrium. So, and actually, you'll probably be mostly toward the ketone side. There'll be a tiny little bit of protonated ketone, but that little bit of protonated ketone is highly reactive, and so it reacts with. We can either choose to get the azide anion that we've just kicked out or the hydrozoic acid. I'm not too fussy about which one. There'll be more hydrozoic acid species in solution, so probably technically we would want to take one of these forms we've got here and make them be the nucleophile. So for example, that would be how hydrozoic acid can attack this molecule. Okay, there we go. So overall, we started with a protonated ketone, so it had a positive charge, and hydrozoic acid is neutral. And our intermediate we've just drawn has one positive charge. So that's good. It's good when you're drawing a mechanism to just check every now and then, do my charges make sense? If I have a neutral molecule to start with, do I end up with a neutral molecule after my curly arrows? So to get from that to the intermediate that we've drawn there, we need to lose a proton and lose this OH group. So it's likely that we will make this a better leaving group first. So we could just do that with hydrozoic acid again, like that. And I'm going to do it in the long-winded form. Now I've made a little bit of a mistake here because I've got a molecule with a positive charge and I'm protonating it to make it a molecule with two positive charges, and that's not a great idea. So if I had an eraser, I'd erase this. I've got a pen that will erase it. So at this stage of answering the exam question, I'm going, oh, this is not bad, but I could probably do better. So let's get rid of that. Okay. And let's get rid of this positive charge first before we kick out the OH group as a leaving group. So we can do that. If we want to be really pedantic about it, we'll have some kind of proton transfer. So we could have, for example, water come in and remove that proton. Okay, so what do we get out of that? Okay, so we have this, and now this nitrogen has two lone pairs and two bonds, and so therefore has a formal negative charge. So overall the molecule is now neutral. And what we can do is that protonation that I wanted to do before. So we're going to take probably hydrozoic acid again. Okay, there's our really good leaving group of water, and we've still got that azide group here. Okay, now we've got a good leaving group, so we can just make that depart. But why isn't it drawn the same as I drew it in intermediate at the start of the question? Well, we can get to that structure by just helping that group to depart by pushing in a pair of electrons from that nitrogen of the azide. And so we can go straight to that really stable looking, or more stable looking resonance form by doing that. So that takes us to the intermediate. So I'll redraw that here. Okay, now that intermediate is going to be pretty unstable because we've got an NN triple bond with a positive charge on that central nitrogen, and if we kick electrons towards that, we're going to spit out N2 as the leaving group. That's one of the most stable leaving groups we can possibly imagine. So that is going to depart like this, and but that would give us a positive charge on this nitrogen here, and a not very stable looking cation. So what happens is that departs at the same time as this R group migrates. And this is where it's really very similar to the Beckmann rearrangement and the Curtius rearrangement. We've got a group migrating to nitrogen at the same time as a leaving group departs. Okay, so if we draw out the product of that, I'll just squeeze it into this last little bit of room here. I'm going to draw it not in realistic looking bond angles, just to keep it as similar looking to what we started with. So we're going to have this. That bond to the R group is now missing, so we're going to have a carbocation there, and we've lost nitrogen. So we may as well put that over the arrow. And now remember, this starting material had lone pair on nitrogen. This has a lone pair on nitrogen as well, and we've said before, and you would have seen before, that heteroatoms next to a carbon with a positive charge are able to stabilize that positive charge through resonance. So we can push that pair of electrons in to make a triple bond. And now I'm going to draw this in a more realistic arrangement. Actually, I'm going to make a bit more room for it. Okay, remember this position here is a carbon atom, even though I haven't drawn it in, there's a carbon there. And we've now got that nitrogen with 4 bonds. It's used its lone pair to share that with the carbon next to it. So now it has a formal positive charge. And this whole structure, that's 2 resonance contributors to the overall structure of this intermediate, which we call a nitrillium or nitrillium ion. Okay, so it's more stable than a typical carbocation because of the nitrogen, but it's still a carbocation, so it's still quite high energy, and it will be captured by a nucleophile. And in this case, it gets captured by water because the reaction's done in an excess of water. That's the sort of most likely nucleophile to capture it. Okay, so we're going to capture at that carbon. That would make that carbon pentavalent. So we have to break one of the bonds to that carbon and push electrons towards that positive charge. It's like an electron sink. It's the end of the Kelly-Arrow sort of cascade. So that will give us a molecule that looks like this. That carbon there now has that. Okay, now to get to our final product, amide, we're going to do some proton transfers and tautomerism. So if we lose a proton from this, minus H plus, we get to that, and that's just the tautomer of an amide. And I think this question is really all about the earlier part of the mechanism. It's about spotting how you get to that intermediate and how it rearranges through this Schmidt rearrangement. The last bit, the tautomerism, you can look that up in a textbook or online. There's lots of mechanisms, so I'll just show that and say the word tautomerism or tautomerization, I guess is the more accurate term. And that's how we get from this this tautomer to the amide tautomer, which is much more stable, because you have that nice strong CO double bond. It's very highly polarized because of the nitrogen next door. Okay, so that is talked about earlier, but hopefully you can recognize the key components of this question are to recognize that the ketone is going to be protonated to make it more reactive. It's going to be attacked by the hydrozoic acid. We're going to lose water to make that high energy intermediate. We're going to get migration of one of those R groups. And in this example, we've just given generic R groups, so it doesn't really matter what we migrate. And we won't go into, like, in depth, is there a preference for one over the other? We're just given the product, and we can just show the appropriate group migrating. And then once that group migrates, to spot that the nitrillium ion or nitrillium ion is stabilized, and so there's more than one resonance form, and you can draw out both of those, and you want to draw out both of them to get full marks in an exam situation. And then finally, that the product after water captures that is going to tautomerize to a nice stable amide. So hopefully that helps you draw out the mechanism of a Schmidt rearrangement and helps to show you how these migrations toward nitrogen atoms occur. Okay, thanks.